Okay, we're looking at the operation of the Class C amplifier, and here we have an amplifier that we might call a Class C amplifier, and it's just a transistor feeding some kind of matching network, maybe with a resonant tank, and we're looking at the relationship of the drain current with respect to the input voltage. And with the Class C, we bias the input such that the drain current doesn't conduct until we reach a certain voltage. So our drain current should be pretty close to zero, and usually we have to go past even the threshold voltage of the transistor because we biased the transistor into a gate to a negative voltage. Now once we get to this turn-on voltage, the current should start to conduct and should be fairly linear. So if we look at the slope of this current versus voltage characteristic, this is equal to the GM of the device, which is the transconductance. And this makes sense. Transconductance is a measure of the voltage versus current, or the current versus voltage characteristic of a device. So here we can say that ID is equal to 0, or VI is less than some predetermined voltage, which we'll call Vx, and it's equal to GM for VI is greater than that Vx. If we look at the characteristic, if we look at the current waveform with respect to time, we would see it would look something like so. Up to some omega t equal to half the conduction angle. And remember, the full conduction angle, theta, is less than 180 degrees. That's what defines it as a Class C amplifier. We're assuming this is periodic, so it would repeat in time. So if we see up to that conduction angle of theta equals 2, we can start doing some derivations. So we know that VI, or input waveform, is equal to VA cosine of omega t. At omega t equal to theta over 2, VI is equal to Vx. We can say Vx is equal to VA times cosine of theta over 2, or theta is equal to 2 cosine inverse of Vx over VA. All right, going into the next step of the derivation, we can now say ID is equal to GM times VI minus Vx, which is equal to GM times VA cos of omega t minus VA cos of theta over 2. We can find our DC current, which is equal to 1 over t times the integral of ID with respect to time. This is minus theta over 2 omega to theta over 2 omega. Okay, and if we use our calculus to finish this integral, we can show that IDC is equal to GM times VA divided by pi times sine of theta over 2 minus theta over 2 times cosine theta over 2. And if theta is constant, the DC current is linearly proportional to VA. Okay, so we can also show that IDC is equal to 0 for theta is equal to 0. So saying if the conduction angle is 0 degrees, then we don't have any DC current. And that makes sense as to why the efficiency goes to 100%, because we don't have any DC current, we're not burning any power. So we can also look at what the power is at random harmonic content. So we can ask ourselves, what is the power output for PA at different harmonic frequencies? And the way that we're going to figure this out is to use Fourier series analysis. Okay, so we're going to find the current at the nth harmonic of the frequency omega, and this is equal to 2 over t times the integral over t id cosine of n omega t. And we can make our substitutions and perform the integral, and if we do so, and this is a fairly complicated integral, we would get the following result. Okay, so we should have the following expression. So we can find the fundamental current by substituting n is equal to 1, that's the desired signal, and we can plug in any n that's higher than that to find the distortion products at higher frequencies. Okay, so the reason that we showed this amplifier as having a tank circuit is that the filtering at the output removes harmonic distortion, so that the only power delivered to the load is at the fundamental frequency. Of course, the filter that we would need, we would have to have a very high quality factor to realize this. Okay, so in the next set of notes, we will finally calculate what the efficiency of the amplifier